Imagine standing on the edge of humanity's greatest frontier, looking up at a celestial body that has captivated our species for millennia, and realizing that the pale sphere hanging in our night sky isn't just a romantic symbol or a distant curiosity. It's a treasure chest worth trillions of dollars, floating just 3 days away from Earth. The moon, that ancient companion that has witnessed every triumph and tragedy of human civilization, holds within its lifeless surface resources so valuable, so transformative, that they could reshape the global economy, solve our energy crisis, and determine which nations will dominate the next century. But here's what should keep you awake at night. Right now, as you hear these words, a new space race has already begun. And unlike the Cold War competition that put the first humans on lunar soil, this race isn't about planting flags or proving ideological superiority. This is about cold, hard profit. This is about power. This is about who will control the resources that could be worth more than the entire gross domestic product of the United States. The question isn't whether we'll mine the moon. The question is who will get there first, who will make the rules, and whether you'll be living in a world transformed by lunar resources or left behind in an outdated economy while others leap centuries ahead. Are you ready to understand what's really at stake? The year is 2024, and something unprecedented is happening in the space industry. While most people scroll through their phones, unaware of the shift occurring above their heads, multiple nations and private companies quietly position themselves for what experts are calling the most significant economic opportunity in human history. NASA's Artemis program isn't just about exploration anymore. China's Chang'e missions aren't purely scientific endeavors. SpaceX isn't building Starship just to visit Mars. They're all preparing for the same thing, extracting resources from the moon. And the numbers are staggering. Conservative estimates place the total value of mineable lunar resources at over $1 quadrillion. Yes, you heard that correctly. 1 quadrillion. That's a 1 followed by 15 zeros. To put that in perspective, that's roughly 13 times the entire global economy as of 2024. But even that astronomical figure might be underselling it, because there's one particular element on the moon that could fundamentally change everything about how our civilization produces energy. Have you ever heard of helium-3? Most people haven't, and that's exactly why this story is so important. On Earth, helium-3 is extraordinarily rare, so scarce that we measure our planetary supply in kilograms. But on the moon, it's abundant. Scientists estimate there are over 1 million metric tons of helium-3 embedded in the lunar regolith, the fine dust that covers the moon's surface. Why does this matter? Because helium-3 is the perfect fuel for nuclear fusion reactors. Unlike the nuclear fission we use today, which produces dangerous radioactive waste and uses uranium and plutonium, fusion using helium-3 produces almost no radiation, no long-lived radioactive waste, and releases enormous amounts of clean energy. A single space shuttle cargo bay full of helium-3, roughly 25 tons, could power the entire United States for 1 year. Let that sink in. One shuttle load. 1 year of power for 330 million people. The economic implications are beyond comprehension. Each ton of helium-3 has been valued at around $3 billion based on its energy generation potential. Do the math. 1 million tons at $3 billion per ton equals $3 quadrillion, just from this one element alone. But before you start thinking this sounds too good to be true, like science fiction or wishful thinking, consider this: the technology to mine lunar helium-3 is not theoretical. It's not decades away. The primary challenge is simply getting there and establishing infrastructure. The extraction process is actually straightforward compared to mining on Earth. You heat the lunar regolith to about 700 degrees Celsius. The helium-3 is released as gas. You collect it, liquefy it, and transport it back to Earth. We've known how to do each of these steps for decades. The Chinese space program has explicitly stated that helium-3 extraction is a long-term goal of their lunar missions. In 2019, China became the first nation to land on the far side of the moon with their Chang'e 4 mission. In 2020, They successfully returned lunar samples to Earth with Chang'e 5, the first sample return mission in over 40 years. These aren't random achievements. They're methodical steps in a carefully planned strategy. Ask yourself, what would your country's position in the global economy be if another nation controlled the primary source of clean, unlimited energy? What leverage would that provide? What dependencies would that create? Beyond helium-3, the moon harbors resources that sound mundane until you understand the context. Water. Yes, water. In 2020, NASA confirmed what scientists had suspected for years. There's far more water ice on the moon than previously thought, and it's not just hiding in permanently shadowed craters at the poles. It's distributed across the lunar surface, locked in the soil. This discovery, made by the Stratospheric Observatory for Infrared Astronomy, or SOFIA, detected water molecules in Clavius crater, one of the largest craters visible from Earth. The concentrations range from 100 to 412 parts per million, roughly equivalent to a 12-ounce bottle of water per cubic meter of soil. Now, that might not sound like much, but the implications are revolutionary. On Earth, water is heavy, and launching heavy things into space costs approximately $10,000 per kilogram with current technology. Water is essential for human survival, obviously, but it's also the key to everything else in space. You can split water into hydrogen and oxygen. Hydrogen and oxygen combined are one of the most powerful rocket propellants we know. Oxygen is what astronauts breathe. Hydrogen can be used in fuel cells for power. Water shields against radiation. Suddenly, the moon isn't just a destination. It's a gas station. It's a life support system. It's a launching point for missions deeper into the solar system. Think about the physics for a moment. Earth's gravity well is deep. Getting off our planet requires enormous energy, massive rockets, incredible fuel loads. The moon's gravity is only 1/6 of Earth's. Launching from the lunar surface requires a fraction of the energy. If you could refuel spacecraft on the moon using resources extracted right there, you've just made missions to Mars, to the asteroid belt, to the outer solar system exponentially cheaper and more feasible. NASA's plan for the Lunar Gateway, a space station orbiting the moon, explicitly incorporates this strategy. The Gateway isn't just an observation post. It's infrastructure for a lunar economy. SpaceX's Starship is being designed to refuel in orbit and on other celestial bodies. The entire architecture of humanity's expansion into the solar system depends on not bringing everything from Earth. It depends on living off the land, or in this case, living off the moon. But let's dig deeper into what else lies beneath that gray, cratered surface. Rare earth elements. These are materials with names you've probably never heard but that define modern technology. Neodymium, europium, terbium, dysprosium, yttrium. They're in your smartphone, your computer, electric vehicle motors, wind turbines, LED lights, medical imaging devices, precision-guided weapons. They're called rare earth, not because they're necessarily scarce in Earth's crust, but because they're extremely difficult to extract and process. The mining and refining processes are environmentally devastating, producing toxic waste and requiring enormous amounts of water and chemicals. China currently controls about 70% of global rare earth production and 90% of processing, giving them tremendous economic and strategic leverage. In 2010, during a territorial dispute with Japan, China briefly restricted rare earth exports, causing global prices to skyrocket and sending shockwaves through technology and defense industries worldwide. That was a warning shot about resource dependency that most people barely noticed. Now imagine this. The moon's surface has been bombarded by asteroids and comets for billions of years. Many of those asteroids were metallic, rich in platinum group elements, rare earth elements, and other valuable materials. When they impacted the moon, there was no atmosphere to burn them up, no water to wash them away, no geological processes to bury them deep underground. They're just sitting there, mixed into the regolith, waiting to be extracted. Studies of lunar samples returned by the Apollo missions revealed significant concentrations of titanium, particularly in the dark regions called Maria, the vast plains of ancient lava flows. Some lunar soils contain up to 10% titanium dioxide, far higher than most terrestrial deposits. Titanium is lightweight, incredibly strong, and resistant to corrosion, making it invaluable for aerospace applications, medical implants, and advanced manufacturing. The Moon also contains aluminum, silicon, and iron in abundance. These aren't exotic materials, but getting them from the Moon to space-based manufacturing facilities would be far cheaper than launching them from Earth. Here's where it gets really interesting. Imagine you're a company that wants to build massive solar power satellites in Earth orbit. These satellites could collect solar energy 24 hours a day without atmospheric interference or nighttime, then beam that power down to Earth using microwaves or lasers. The concept has been studied since the 1960s, and the technology is mature. The only problem has been cost. Building something that large in orbit would require launching thousands of tons of material from Earth at prohibitive expense. But if you could mine raw materials on the Moon, process them using automated facilities powered by abundant solar energy, and then launch the components to Earth orbit at a fraction of the cost, suddenly the economics change completely. This isn't speculation. Companies like Transastra and Carmen Plus are actively developing the technologies for space-based resource extraction and manufacturing. The European Space Agency has funded multiple studies on lunar resource utilization. Japan's space agency, JAXA, has partnered with private companies to develop moon mining technologies. Let's pause and consider the timeline, because understanding where we are in this story requires knowing where we've been. On July 20th, 1969, Neil Armstrong stepped onto the lunar surface and spoke those famous words about one small step. Between 1969 and 1972, 12 American astronauts walked on the Moon across 6 Apollo missions. They collected 382 kilograms of lunar rocks and soil. Then, for reasons both political and economic, we stopped going. The Apollo program was expensive, costing about $25 billion in 1970s money, equivalent to roughly $280 billion in today's currency. The Soviet Union had lost the race, the political motivation evaporated, and public interest waned. The last human to walk on the Moon was Eugene Cernan, commander of Apollo 17, on December 14, 1972. For over 50 years, no human has returned. But here's what changed. Technology got better and cheaper. During those 50 years, we developed autonomous robotics, artificial intelligence, advanced materials, more efficient solar panels, better batteries, reusable rockets. We also learned something crucial about what makes space ventures economically viable. Government programs focused on exploration and prestige are expensive and unsustainable. But if you can identify a profit motive, if you can create a business case, private investment floods in and innovation accelerates. SpaceX proved this with reusable rockets. Before Falcon 9, the idea of landing an orbital-class rocket booster and flying it again was considered science fiction by most aerospace experts. Now it's routine. SpaceX has launched the same booster more than 20 times. That innovation, driven by the profit motive of reducing launch costs, has cut the price of reaching orbit by roughly 70%. Apply that same entrepreneurial energy to lunar resources, and you begin to see why this is happening now. In 2017, President Donald Trump signed Space Policy Directive 1, directing NASA to return Americans to the Moon. In 2020, his administration issued an executive order asserting the right of Americans to engage in commercial exploration and exploitation of space resources, explicitly rejecting the interpretation that space is a global commons, requiring international governance of resource extraction. That same year, NASA announced the Artemis Accords, a framework for international cooperation in lunar exploration. As of late 2023, over 30 countries have signed these accords, agreeing to principles like peaceful exploration, transparency, interoperability, emergency assistance, registration of space objects, release of scientific data, protecting heritage sites, managing space resources, preventing harmful interference, and proper disposal of orbital debris. Notably absent from the signatories, China and Russia, who announced their own partnership for an international lunar research station. Do you see what's happening? The political framework for lunar resource extraction is being established right now. The Artemis Accords essentially create a coalition of nations aligned with American interests and approaches to space resource rights. China and Russia's separate program creates a competing coalition. This isn't Cold War ideology. This is about who sets the legal and economic rules for a multi-trillion-dollar industry. The Outer Space Treaty of 1967, which both groups nominally follow, states that nations cannot claim sovereignty over celestial bodies. The moon belongs to all humanity. But the treaty says nothing explicit about resource extraction by private companies or individuals. It's a legal gray area, and both sides are trying to fill that gap with their own interpretations. The American position is essentially, we can't own the moon, but if we extract resources from it, we own those resources, just like you can't own the ocean, but you can own the fish you catch. Critics argue this violates the spirit of the treaty and creates a loophole where de facto control equals ownership. Here's a thought experiment for you. Imagine two competing mining companies set up operations in the same resource-rich area of the moon. Let's say near Shackleton Crater at the lunar South Pole, where water ice is abundant and there are peaks of eternal light, mountains that receive sunlight almost constantly, perfect for solar power. One company is American, backed by NASA collaboration. The other is Chinese, backed by their space agency. Both claim they were there first, or that their safety zone extends into the other's operations. There's no lunar police force. There's no court with clear jurisdiction. The UN Committee on the Peaceful Uses of Outer Space has no enforcement mechanism. What happens? Do the companies negotiate directly? Do their home countries get involved? Does it escalate? Who decides? These aren't hypothetical questions. They're scenarios that space lawyers and policy experts are actively gaming out right now, because the first lunar mining operations are likely less than a decade away. Let's talk about who's actually preparing to do this. NASA's Artemis program, named after Apollo's twin sister in Greek mythology, plans to land the first woman and first person of color on the moon by 2026, though delays are likely. The program's architecture involves the Space Launch System, the most powerful rocket NASA has ever built, and the Orion crew capsule for transportation. SpaceX's Starship has been selected as the human landing system for the initial missions. The Gateway Station will orbit the moon, serving as a staging point. But unlike Apollo, Artemis is explicitly designed to be sustainable, establishing a permanent presence. NASA has released plans for the Artemis Base Camp, a surface habitat near the lunar South Pole where astronauts could live for extended periods. The agency is also developing the Lunar Terrain Vehicle, essentially a rover that astronauts can drive for kilometers across the surface. China's program is arguably even more ambitious. After successfully landing Chang'e 3 and 4 on the lunar surface and returning samples with Chang'e 5, they've announced plans for Chang'e 6, 7, and 8 missions, culminating in a crewed landing potentially by 2030. Their stated goal is to establish an international lunar research station by 2035, though international, in this context, means their partner Russia and a few other nations in their coalition. Chinese state media has explicitly discussed lunar resource utilization, particularly helium-3, as a strategic objective. Some Western analysts worry that China's rapid progress and stated intentions could lead to a situation where they establish facts on the ground, or rather on the moon, that become difficult to challenge. If Chinese facilities are already extracting water ice from the richest deposits at the South Pole, can other nations simply move in next door? What are the rules? Private companies are equally aggressive. Astrobotic Technology, an American company, has developed lunar landers and plans to deliver payloads to the moon for NASA and commercial customers. In January 2024, their Peregrine lander launched but suffered a propellant leak, failing to reach the moon, a reminder that this is still incredibly difficult. Intuitive Machines successfully landed their Nova C lander on the Moon in February 2024, the first American spacecraft to soft land on the lunar surface since Apollo 17 and the first ever by a private company. iSpace, a Japanese company, has similar ambitions, though their first landing attempt in April 2023 ended in a crash. These early missions are delivering scientific instruments and technology demonstrations, but the business plans explicitly include future resource extraction services. Then there's Blue Origin, Jeff Bezos' space company. Bezos has stated that his long-term vision involves moving heavy industry off Earth entirely, preserving our planet as a residential and light commercial zone while doing mining and manufacturing in space using extraterrestrial resources. Blue Origin is developing Blue Moon, a large lunar lander capable of delivering metric tons of cargo to the surface. Bezos isn't thinking about making money from selling lunar resources back to Earth. He's thinking about using those resources to build things in space for use in space, creating an entirely new economy. This is the distinction between extracting helium-3 to ship home and using lunar oxygen and hydrogen to refuel spacecraft, or using lunar metals to build satellites and habitats. Both models are being pursued by different players. Now, let's address the elephant in the room. Is this actually technologically feasible, or is it hype designed to attract investors? The answer is nuanced. The science and engineering fundamentals are sound. We know where the resources are, we know how to extract them in theory, and we have most of the required technologies already demonstrated at some level. What we haven't done is integrate all these systems and operate them remotely on the Moon at commercial scale. That's not a small caveat. The Moon is a brutally harsh environment. Daytime temperatures in direct sunlight reach 127 degrees Celsius. Nighttime temperatures plunge to negative 173 degrees Celsius. A lunar day lasts 29.5 Earth days, meaning nearly 2 weeks of continuous darkness in most locations unless you're at the poles. There's no atmosphere to shield against radiation or micrometeorites, tiny space rocks that constantly bombard the surface at thousands of kilometers per hour. The dust, that fine regolith, is nothing like Earth sand. It's incredibly abrasive, statically charged, and it sticks to everything. During the Apollo missions, it damaged spacesuits, clogged mechanisms, and proved to be a major operational headache. Mining equipment would have to operate in vacuum conditions with extreme temperature swings. Every component would need to be resistant to abrasive dust. Power systems would need to function through 14-day lunar nights, which means either large battery systems, radioisotope thermoelectric generators using plutonium, or locating at the poles where sunlight is near constant. Processing facilities would need to operate autonomously or with minimal human oversight, because sending people is expensive and risky. You'd need habitats, life support, radiation shielding, food supplies, medical facilities. The distance creates communication delays. Even at light speed, signals take 1.3 seconds to travel from Earth to the Moon, so real-time remote control of equipment isn't possible. Systems need to be autonomous enough to handle unexpected situations. But here's the crucial point. Every one of these challenges has a known solution. Engineers have designed dust-resistant mechanisms and ceramic coatings. We have rovers that operate autonomously on Mars with far longer communication delays. Solar panels and batteries are more efficient than ever. Advanced robotics can perform complex tasks with minimal supervision. The International Space Station has proven we can keep humans alive in space for months or years. These technologies need to be adapted, integrated, and proven in lunar conditions. But we're not waiting for some magical breakthrough. It's engineering, not science fiction. NASA's Commercial Lunar Payload Services program is explicitly designed to demonstrate these technologies through partnerships with private companies. They're sending experiments to test resource extraction, construction techniques using lunar regolith, power systems, communication networks, and navigation systems. One of the most promising technologies is in situ resource utilization, abbreviated as ISRU, which is exactly what it sounds like. using resources found at your location rather than bringing everything from Earth. A perfect example is the production of oxygen from lunar regolith. The moon's soil is between 40 and 45% oxygen by weight, bound up in metal oxides, primarily silicon dioxide, aluminum oxide, iron oxide, and calcium oxide. Several methods can extract this oxygen. One involves heating the regolith with hydrogen to produce water vapor, which you then electrolyze into hydrogen and oxygen. Another uses molten salt electrolysis, where you heat the soil in a molten calcium chloride bath and pass an electric current through it, liberating oxygen gas. The European Space Agency has been developing a prototype that can extract 96% of the oxygen from simulated lunar regolith. If you can produce oxygen on the moon, you've solved half of the propellant equation for rockets and provided the primary consumable that astronauts need. Let's explore one of the most audacious proposals that's actually being seriously considered: asteroid redirect missions launched from the moon. Here's the concept. There are thousands of near-Earth asteroids, many of which are small, maybe 10 to 30 meters in diameter, and some of which are almost pure metal, likely fragments of ancient protoplanets that broke apart billions of years ago. A single metallic asteroid of modest size could contain more platinum group metals than have been mined in all of human history. The problem is their orbits don't bring them close enough to Earth for easy access, and launching a mission to intercept them, extract resources, and return is prohibitively expensive with current technology. But if you had infrastructure on the moon, you could build spacecraft there using lunar materials, fuel them with lunar propellants, and launch them at a fraction of Earth's energy cost. These spacecraft could rendezvous with asteroids, attach to them, and slowly alter their trajectory over months or years using ion drives or other efficient propulsion. You could bring the entire asteroid into lunar orbit, then take your time processing it. NASA has already tested the concept with the OSIRIS-RX mission, which visited asteroid Bennu and returned a sample to Earth in 2023. Private companies like Planetary Resources and Deep Space Industries pursued asteroid mining until they realized the technology and market weren't mature enough, but their research laid groundwork that others are building on. The key insight is that you don't necessarily bring asteroid materials to Earth's surface. The real value is using them in space. If you need metal to build a space habitat or solar power satellite, it's vastly cheaper to get it from an asteroid than to launch it from Earth. The moon becomes the industrial center, the processing facility, the construction yard for the space economy. This brings us to one of the most profound questions hanging over this entire endeavor. What are the environmental and ethical implications? The moon has no ecosystem to damage, no indigenous species to endanger, no atmosphere to pollute. In that sense, it seems like the perfect place for heavy industry. But some scientists and ethicists argue that the moon has intrinsic value beyond economics. It's been unspoiled for billions of years. It's a record of solar system history, with ancient rocks and undisturbed surfaces that tell us about the formation of Earth and the moon, about the bombardment history of the inner solar system, about the solar wind's interaction with airless bodies. Mining operations could destroy scientifically invaluable sites. The far side of the moon, forever facing away from Earth, is uniquely quiet in radio frequencies, making it the perfect location for radio telescopes that could detect signals impossible to hear from Earth. Industrial activity could create electromagnetic interference. The Apollo landing sites are another concern. These are the locations where humans first touched another world. Footprints left in the lunar dust will remain for millions of years because there's no wind or rain to erase them. Flags, equipment, experiments, plaques, the descent stages of lunar modules are all still there. They're not legally protected under any international framework, though the Artemis Accords include a commitment to preserving heritage sites. What happens if a mining operation wants to set up in an area near Tranquility Base, where Apollo 11 landed? Do we treat these sites like historical monuments, establishing protected zones? Who decides how large those zones should be? The moon's surface area is about 38 million square kilometers, similar to Asia's land area, so there's theoretically plenty of room. But the most valuable sites, those permanently shadowed craters with water ice and nearby peaks with constant sunlight, are limited in number. There's also a philosophical dimension that's worth contemplating. For all of human history, the moon has been a symbol, a source of wonder, a presence in poetry, mythology, religion, and art across every culture. It's governed our calendars, inspired our stories, caused the tides that shaped coastal ecosystems and human settlements. What does it mean to turn it into an industrial site? Does something important get lost when we view it primarily as a resource to be exploited? Or is this simply humanity's next step, bringing our tool-using, resource-extracting nature to a new frontier, no different in principle from our ancestors learning to mine copper and iron? These questions don't have easy answers, and different people will have different perspectives based on their values and worldviews. But they're worth asking as we stand on the threshold of this transformation. Consider this scenario, which some researchers have proposed as a genuine possibility. What if aggressive mining operations altered the moon's mass distribution enough to affect its orbit or rotation? This sounds far-fetched, but let's examine the numbers. The moon's mass is about 73 quintillion kilograms. Even if we extracted 1 trillion tons of material, that's only about 1/1,000,000% of its total mass. The gravitational effects would be negligible. However, the moon is tidally locked to Earth, always showing us the same face, because its rotation period matches its orbital period, a stable equilibrium reached over millions of years. If you removed enormous amounts of mass from specific locations, particularly concentrations of dense materials, you could theoretically shift the center of mass enough to destabilize this equilibrium over long timescales. Most physicists believe this is unrealistic even with extensive mining, but it hasn't been rigorously modeled. More importantly, it illustrates how we're entering unknown territory. We've never tried to industrially exploit a celestial body before. There might be second-order effects we haven't considered. Let's shift to the economic models and ask a critical question. How do companies expect to make money from lunar resources given the enormous upfront costs? The capital investment required to establish lunar mining operations is staggering. Estimates range from tens of billions to hundreds of billions of dollars depending on the scale and approach. You need to develop and launch equipment, establish infrastructure, prove the extraction and processing techniques, create transportation systems, all before you've returned a single dollar of revenue. Traditional venture capital isn't suited for investments that might not pay off for decades. So who's funding this? The answer is a combination of government contracts, patient private investment, and a bet on dramatically decreasing launch costs. NASA's Artemis program represents about $93 billion through 2025 for developing systems like the Space Launch System, Orion, and supporting infrastructure. Some of those contracts go to companies like SpaceX and Blue Origin, subsidizing their development of technologies that have commercial applications. China's space program is state-funded as a strategic priority. Private companies are pursuing a mixed model. Secure government contracts for delivering payloads and services, use that revenue to develop technologies, attract investors willing to take long-term positions based on the potential returns, and count on launch costs continuing to decrease. This is where SpaceX's Starship becomes crucial to the whole equation. Starship is designed to be fully reusable, capable of carrying over 100 tons to orbit and being refueled there for trips to the Moon, Mars, or beyond. If Starship achieves its design goals, the cost of sending payloads to the Moon could drop by an order of magnitude or more compared to current systems. Elon Musk has claimed that Starship could eventually reduce launch costs to as low as $2 million per flight, though many experts are skeptical of such aggressive targets. Even if the actual cost is 10 or 20 times higher, it would still represent a revolutionary decrease. At those prices, the economic calculations for lunar mining change fundamentally. Here's a specific business case that's been analyzed. Imagine a company establishes a facility at the lunar South Pole that extracts water ice and processes it into liquid hydrogen and liquid oxygen propellant. Spacecraft traveling from Earth orbit to Mars or the asteroid belt could stop at a lunar depot to refuel. Because the fuel is produced on the Moon, It doesn't have to be launched from Earth at enormous cost. The company charges, say, $5,000 per kilogram for propellant delivered at the lunar depot. Far cheaper than launching it from Earth, but expensive enough to generate profit. A typical Mars mission might require 100 tons of propellant for the Earth-Mars leg. That's $500 million in revenue per mission. If there are multiple Mars missions per year, plus asteroid missions, plus satellites being deployed in high orbits, the market becomes substantial. This isn't hypothetical daydreaming. NASA has commissioned studies on exactly this model because it makes their deep space exploration cheaper. The helium-3 business case is even more speculative, but potentially far more lucrative. The challenge is that fusion reactors using helium-3 don't exist yet as commercial power sources. We've achieved fusion reactions in laboratories and demonstrated net energy gain very recently. But commercial fusion power plants are likely still decades away. By the time they're ready, will lunar helium-3 be available? That's the bet some companies and governments are making. China's investment in lunar exploration with explicit interest in helium-3 suggests they believe fusion power will become viable and that securing access to fuel sources now provides strategic advantage later. If they're right, and if fusion becomes the dominant energy source of the late 21st century, controlling helium-3 supplies would be roughly equivalent to controlling oil supplies in the 20th century. The geopolitical implications are enormous. Rare earth elements present a different economic puzzle. They're valuable but much heavier than helium-3 relative to their value. Bringing them back to Earth might not make economic sense when you factor in transportation costs. However, if political tensions escalate and terrestrial rare earth supplies become restricted through export controls or conflict, the calculus changes. National security concerns could justify costs that pure market economics wouldn't. The United States has already identified rare earth dependency as a strategic vulnerability. Multiple government reports have recommended developing alternative sources. The Moon is the ultimate alternative source, immune to geopolitical instability because, well, it's not on Earth. Now let's explore some fascinating technical details that really illustrate how this could work. One of the most elegant proposed mining techniques involves solar concentrators, essentially giant mirrors that focus sunlight onto lunar regolith. Remember, sunlight on the Moon, without any atmospheric filtering, is intense. By concentrating it with mirrors, you can heat soil to extremely high temperatures, causing volatiles like water, helium, and other elements to vaporize and be collected. The equipment is relatively simple: reflective surfaces, structures to hold them, and collection systems. You could even manufacture the mirrors on the Moon using lunar aluminum and silicon. The whole system runs on solar power, no fuel needed, and can operate for years with minimal maintenance. Teams at NASA and various universities have built prototypes and tested them on simulated lunar regolith with promising results. Another intriguing approach involves microwave heating. Microwave energy can penetrate into the regolith, heating it from within, which might be more efficient than surface heating in some cases. The water vapor or other volatiles rise up through the soil and can be captured with cold traps. Surfaces kept at extremely low temperatures where gases condense back into solids or liquids. The Moon's nighttime temperatures provide those low temperatures naturally. Some designs propose mining during the lunar day with heat-based extraction, then using the lunar night for cold trap collection, working with the environment's natural cycles rather than fighting them. For metals, the most developed concept is molten regolith electrolysis. You heat lunar soil until it melts, about 1,400 degrees Celsius for typical compositions, then pass electric current through the molten material. Oxygen bubbles off as gas at the anode, which you collect. At the cathode, metal alloys accumulate. You end up with oxygen, which is useful, and a mixture of iron, aluminum, silicon, and other metals, which can be further processed or used as is for construction. The Apollo missions returned samples showing that lunar regolith melts into a glass-like substance that's actually quite strong. Researchers have proposed using this material, called lunar concrete, for building landing pads, roads, and even habitat structures, melting it into shape with solar concentrators or microwave systems. 3D printing with lunar regolith is another area of intense research. The European Space Agency partnered with architecture firms to design printable habitats using lunar soil as the raw material. The idea is to send a relatively small printer, have it scoop up regolith, process it into a printable form, possibly by melting it or mixing it with a binding agent, then layer by layer construct structures. This could build habitats for astronauts, protective walls to shield against radiation and micrometeorites, storage facilities, garages for equipment, whatever is needed. The advantage is you're not launching building materials from Earth. A printer and some basic components might mass a few tons, but it could construct facilities massing hundreds of tons using local materials. Let's pause and consider what daily life might look like for the first lunar miners. Imagine you're part of a crew stationed at Shackleton Crater for a 6-month rotation. You live in a habitat partially buried in regolith for radiation protection. The walls are thick, made from lunar concrete printed by robots before you arrived. Inside, the environment is pressurized to normal Earth atmosphere, temperature controlled, with hydroponics providing fresh vegetables to supplement packaged food. Your work involves supervising automated mining equipment, performing maintenance that robots can't handle, troubleshooting problems, conducting geological surveys to identify the richest deposits. You wear a spacesuit every time you go outside, but it's more advanced than Apollo suits, more flexible, with better life support, designed for extended use. The darkness during work periods is absolute, broken only by your suit lights and the glow from facility lights. The stars are unbelievably brilliant, never twinkling because there's no atmosphere, just steady points of light against absolute black. Earth hangs in the sky, a blue and white marble, rising and setting over the course of a month as the moon rotates. You can see weather systems swirling across the planet's face, continents visible through gaps in clouds. It's beautiful and lonely. Communication with Earth has a delay, so conversations feel stilted. You send messages and wait seconds for responses. Emergencies are terrifying because help is 3 days away at minimum. Your crew is everything. You depend on them, and they depend on you. Psychologically, the isolation is challenging. Studies of Antarctica stations, submarines, and the International Space Station give us some idea what to expect, but the moon is more remote than any of those environments. Crew selection would emphasize mental resilience, compatibility, ability to handle stress and monotony. Entertainment options would be limited to what digital content you brought and whatever you can create. Some propose that lunar bases would have viewing domes where you can sit and watch Earth, a connection to home. Others suggest virtual reality systems to create the illusion of being in natural environments, forests, beaches, familiar places. The work itself would be demanding but possibly rewarding. You're part of something historic, the opening of a new world to human industry. Your labor is directly contributing to making humanity a multi-planetary species. That sense of purpose might sustain people through hardship, or it might not. Turnover could be high. Some people might go once and never want to return. Others might find that they prefer the moon to Earth, that the frontier appeals to something deep in their nature. We'll learn, probably through difficult experience, what works and what doesn't in sustaining lunar communities. There's a darker scenario that's worth considering, not as a prediction but as a possibility to be aware of. What if labor conditions on the moon become exploitative? Workers are isolated, dependent on their employer for life support, transportation, everything. There's no local government, no regulatory agencies, no unions easily able to organize. Companies could potentially impose harsh conditions, long hours, minimal pay, knowing that workers have limited alternatives. Science fiction has explored this theme extensively, but we have historical precedents on Earth. Company towns during the Industrial Revolution, mining camps in remote areas, early colonial settlements often saw exploitation of workers by powerful entities that controlled all resources. International labor standards and oversight would need to be established proactively. The Outer Space Treaty requires that nations are responsible for their citizens' activities in space, including private companies, and must authorize and supervise them. In theory, a lunar mining company based in the United States operates under U.S. jurisdiction and must follow American labor laws. But enforcement from 250,000 miles away is challenging. If a company is violating safety regulations or worker rights, who inspects? Who punishes? These legal frameworks are being developed now, and it's crucial that they include strong protections, because once people are living and working on the moon, revising those frameworks becomes much harder. Let's explore the scientific discoveries that lunar mining might enable as a secondary benefit. Every dig into lunar regolith is an opportunity for geology and planetary science. The moon's surface is a 4 billion-year record of solar system history. Impact craters reveal subsurface layers. Rocks contain isotopes that tell us about the moon's formation. The giant impact hypothesis that suggests the moon formed from debris when a Mars-sized object collided with early Earth. Mining operations could uncover samples from depths that haven't been exposed in billions of years, offering pristine data about ancient conditions. Water ice in permanently shadowed craters might contain organic molecules delivered by comets, giving us insights into the chemistry that led to life on Earth. There's even speculation that lunar regolith could contain traces of Earth's ancient atmosphere. Here's the theory. For billions of years, Earth's atmosphere has been slowly stripped away by solar wind and impacts. Some of those atmospheric molecules might have reached the moon and been implanted in the regolith. If we could identify and extract them, we'd have samples of Earth's atmosphere from different geological eras, including periods before we have any ice core or geological records. We could study the atmosphere from when life first evolved, from mass extinction events, from dramatic climate shifts. This is highly speculative, and the concentrations would be incredibly low, but lunar mining operations sifting through enormous amounts of regolith might accumulate enough material to make it feasible. Another profound possibility, the moon as an archive. Some researchers have proposed that we should use lunar facilities to store backup copies of Earth's biological, cultural, and scientific heritage. A vault buried deep in lunar regolith, in a geologically stable area, protected from radiation and temperature extremes, could preserve DNA samples, seeds, cultural artifacts, digital copies of books and art, scientific data, essentially a backup of human civilization. It sounds paranoid until you consider existential risks: asteroid impacts, nuclear war, pandemics, climate catastrophe. Earth has one basket, and we're putting all our eggs in it. A lunar archive would ensure that even in the worst-case scenario, information about what we were, what we learned, what we created, would survive. The Svalbard Global Seed Vault in Norway serves a similar function, protecting crop diversity against agricultural catastrophe. A lunar equivalent would be the ultimate long-term insurance policy for humanity. The timeline for when all of this might happen is a subject of intense debate. Optimists point to the rapid pace of recent progress and suggest that initial mining operations could begin by the early 2030s, with significant scale by mid-century. NASA's publicly stated goal is to establish sustainable lunar exploration by the end of this decade, which means infrastructure that supports continuous or frequent human presence. China's timeline suggests crewed landings by 2030 and a research station by 2035. Private companies working on lunar landers and resource extraction technologies are targeting the late 2020s for early demonstration missions. Skeptics note that space programs are notorious for delays and cost overruns. The Space Launch System, originally supposed to launch by 2017, didn't fly until November 2022. The James Webb Space Telescope was proposed in the late 90s for a 2007 launch at about $1 billion. It actually launched in 2021 at nearly $10 billion. Major space initiatives are incredibly complex, and complexity breeds delays. Furthermore, the economic case for lunar mining requires not just the technology but also the market. If fusion power doesn't materialize, the helium-3 market doesn't exist. If launch costs don't decrease as hoped, the economics don't work. If international cooperation breaks down and we see conflict over lunar resources, the whole endeavor could stall. A realistic middle ground projection might be demonstration missions in the late 2020s showing resource extraction is possible, small-scale commercial operations in the 2030s focused on supporting space infrastructure like providing propellant for deep space missions, expanding scale in the 2040s as technology matures and markets develop, and by mid-century, a genuine lunar economy with multiple companies, permanent settlements, and significant resource flows. Whether materials ever flow back to Earth in large quantities or stay in space to support orbital industries and Mars missions is an open question that depends on how different technologies and markets develop. There are wild card scenarios that could accelerate everything dramatically. Suppose asteroid mining companies succeed in capturing a small metallic asteroid and demonstrating that it contains quadrillions of dollars worth of platinum and rare metals. Suddenly, investor interest in space resources explodes, capital floods in, and the moon becomes a critical piece of infrastructure for asteroid operations. Or imagine a breakthrough in fusion technology demonstrates commercial viability, and nations scramble to secure helium-3 supplies, triggering a crash program of lunar development. Or geopolitical tensions escalate, and lunar resources become militarized, with nations rushing to establish presence to deny access to rivals. This is the scenario that worries many space policy experts, because it could lead to conflict and undermine the peaceful international cooperation that has characterized space exploration for decades. The militarization question deserves serious attention. The Outer Space Treaty prohibits placing nuclear weapons or weapons of mass destruction in orbit or on celestial bodies and limits the use of the moon and other celestial bodies to peaceful purposes. But peaceful has been interpreted to mean non-aggressive, not necessarily non-military. Satellite reconnaissance is military but not aggressive, for example. Could nations establish military bases on the moon, ostensibly to protect their mining operations? Could lunar resources be used to support military space capabilities? The treaty doesn't clearly prohibit this, and the strategic advantages would be significant. Launching from the moon avoids Earth's deep gravity well, making it easier to position assets throughout cislunar space, the region between Earth and the moon. Imagine kinetic weapons launched from the moon. Simple metal rods that you drop toward Earth, accelerating in its gravity well, hitting with the force of explosives but containing no explosives, just pure kinetic energy. These have been theorized as rods from God, and would be devastating, nearly impossible to defend against because they're moving so fast and contain no electronics to jam or explosives to detect. The Outer Space Treaty would likely prohibit stationing such weapons in space, but defining what constitutes a weapon becomes tricky. A mass driver designed to launch or containers off the moon could theoretically launch other payloads. A facility processing rocket propellant has dual-use potential. The ambiguity creates risks. The best hope for preventing lunar militarization is strong international norms and transparency measures. The Artemis Accords include commitments to transparency and deconfliction, sharing information about where you're operating to avoid harmful interference. If these norms take hold and are respected, they create a framework where everyone knows what everyone else is doing, reducing suspicion and the security dilemma where one nation's defensive moves appear threatening to others, triggering an arms race. But this requires trust and verification, neither of which are easy when strategic interests worth trillions of dollars are at stake. Let's consider a question you might be asking yourself. What does this mean for me, personally, for ordinary people on Earth who aren't astronauts or billionaire space entrepreneurs? The answer depends on how lunar resources are managed and who benefits from them. In the best-case scenario, lunar mining provides cheap, clean energy through helium-3 fusion, reducing energy costs worldwide, mitigating climate change by replacing fossil fuels, and lifting billions of people out of energy poverty. It creates entirely new industries and jobs, not just for engineers and astronauts, but for everyone involved in the supply chains, from manufacturing components to providing services for workers, from legal and financial services to entertainment and media. Economic growth from space resources could fund social programs, education, Healthcare. In a less optimistic scenario, the wealth generated by lunar mining concentrates in the hands of a few corporations and nations that got there first, exacerbating inequality. Energy from helium. 3 might be cheap to produce but expensive to access due to monopolistic control. Nations without space capabilities become more dependent on those that have them, creating new forms of economic colonialism. The jobs created are highly specialized, requiring skills that much of the population doesn't have, and automation means fewer jobs than previous industrial revolutions created. The benefits flow upward while the risks, like debris from increased space traffic or geopolitical tensions, are shared by everyone. Which scenario unfolds depends on choices being made right now about governance, equity, and the legal frameworks for space resources. The principle that space is the province of all humankind, enshrined in the Outer Space Treaty, suggests that benefits should be shared broadly. But translating that principle into concrete policies is the challenge. Some have proposed an international fund where companies pay royalties on resources extracted, and those funds support development in countries that can't participate directly in space activities. Others suggest technology sharing requirements, so that innovations developed through space programs are available globally. These ideas face resistance from companies and nations that argue they're taking the risks and making the investments, so they should reap the rewards.
Your voice matters in this debate.
Space policy isn't determined solely by governments and corporations. Public opinion influences what's politically feasible. If people demand that lunar resources be managed as a common heritage, that environmental and ethical considerations be prioritized, that benefits be equitably shared, policymakers respond. Conversely, if the public is disengaged, decisions get made by narrow interests pursuing their own agendas. The next decade is when the foundational rules for the space economy are being set. What happens in this brief window could shape the next 1,000 years of human civilization. Think about that for a moment. Decisions being made in the next 10 years will determine whether humanity expands into the solar system as a unified species sharing resources and benefits, or as competing factions replicating the conflicts and inequalities of Earth in space. They'll determine whether we treat celestial bodies as sacred, untouchable wilderness, as resources to be carefully managed, or as materials to be exploited without restraint. They'll determine who gets to go, who benefits, and what we become as we take this step. Let's explore some of the most fascinating proposed technologies that sound like science fiction but are being seriously developed. Electromagnetic railguns to launch payloads off the lunar surface. Since there's no air resistance, you could build a long track, accelerate a package to escape velocity using magnetic forces, and fling it toward Earth or into orbit. No rocket fuel needed, just electricity, which you can generate with solar panels. Engineers have calculated that a railgun a few kilometers long could do this, and while no one has built a full-scale version, small prototypes have demonstrated the principle. The payloads would have to be packaged to survive brutal acceleration, but raw materials or processed elements could handle it. Space elevators are much easier on the Moon than on Earth. Earth's gravity and the need for materials stronger than anything we currently have make terrestrial space elevators impractical with present technology. But the Moon's lower gravity and lack of atmosphere change the equation. A cable made of materials we can already produce, like Kevlar or Xylon, could stretch from the lunar surface to a counterweight in orbit. You'd use electric climbers to move payloads up and down. The energy cost is far lower than rockets, and the system can operate repeatedly. Studies by groups like Liftport and researchers at various universities have outlined detailed designs. Self-replicating robots, sometimes called von Neumann machines after the mathematician who proposed the concept, represent the ultimate in autonomous lunar development. The idea is to send a single sophisticated robot that can mine raw materials, process them, manufacture components, and build copies of itself. Those copies build more copies, growing exponentially. Within a relatively short time, you'd have an army of robots constructing whatever infrastructure you need. The initial investment is high because that first robot has to be incredibly capable, but the payoff is enormous. This is very long-term and raises profound questions about control and ethics, but small steps are being taken. Robots that can repair themselves using available materials, or that can manufacture simple components, are in development. Fusion-powered spacecraft using helium-3 mined from the moon could revolutionize solar system exploration. Current chemical rockets are limited by the energy density of their fuel. Ion drives are efficient but produce very low thrust. Fusion offers both high energy density and efficient use of fuel, enabling fast travel times to Mars, the outer planets, even the outer solar system. A fusion-powered spacecraft could reach Mars in weeks instead of months, the outer planets in months instead of years. This isn't just about speed, it's about safety. Radiation exposure is a major risk for long-duration space travel. Shorter trips mean less exposure. It's also about feasibility. The psychological and physiological challenges of spending months in a cramped spacecraft are significant. Reducing travel time makes crewed missions much more practical. The moon could become a shipyard where these fusion-powered craft are built and fueled. Think of it as a port city in the age of sail, where ships were constructed and provisioned before setting out across the ocean. Lunar orbit or the lunar surface would be where spacecraft headed for the outer solar system stop to refuel, take on supplies, and make final preparations. This transforms the economic geography of the solar system. Instead of everything going to and from Earth, you have hubs and nodes, with the moon as a central hub. Some visionaries go even further and imagine terraforming the moon, giving it an artificial atmosphere and perhaps even liquid water on the surface. This is far beyond current technology and might not even be physically possible. The moon's low gravity makes holding onto an atmosphere difficult. Gases would escape into space over time. You'd need to continuously replenish it, perhaps by releasing volatiles from the interior or importing them from comets or icy moons. The energy requirements would be staggering. Most scientists view lunar terraforming as impractical at best, but the fact that serious researchers have studied it shows the scope of thinking about the moon's future. More realistic are large enclosed habitats, pressurized environments that could support ecosystems and large populations. Imagine domes or underground caverns kilometers across, with artificial lighting mimicking daylight, parks, trees, water features, entire towns inside. Getting to that scale requires enormous construction capabilities, but if you're using lunar resources, the materials are available. The main limits are energy and time. With fusion power from helium-3, energy becomes abundant. With self-replicating construction robots, time compresses. By the 22nd century, such habitats might house tens of thousands of people, functioning as true settlements rather than temporary outposts. What would culture be like in these lunar communities? Would they develop distinct identities, separate from Earth cultures? History suggests they would. Isolated or semi-isolated populations develop unique languages, customs, values shaped by their environment and experiences. Lunar settlers would share the experience of living in an artificial environment, of seeing Earth as a distant object rather than the ground beneath their feet, of relying absolutely on technology for survival. This might create a culture that values engineering and science highly, that sees nature as something to be carefully controlled, that emphasizes collective responsibility because individual failures endanger everyone. There might also be physical adaptations over generations. Humans born and raised in 1/6 gravity might develop differently, growing taller with less muscle and bone density optimized for lunar conditions. Returning to Earth could become difficult or impossible for them. Would they even consider themselves Earthlings? Or would they be Lunarians, a new branch of humanity? This raises bioethical questions. Should we be creating populations that can't survive in Earth's gravity? Is that a form of irreversible harm? Or is it simply adaptation to a new environment? No different than populations adapting to high altitude or Arctic cold over generations. The legal status of people born on the moon is unclear under current law. Are they citizens of their parents' nations? Does the location of birth matter when that location isn't sovereign territory of any nation? Could a lunar settlement declare independence, forming a new country? The Outer Space Treaty says nations can't claim sovereignty over celestial bodies, but it doesn't address whether populations living there could assert self-determination. This might seem like a distant concern, but if permanent settlements are established in the 2030s, children will be born there by the 2040s. By the 2060s, you could have a generation of adults who were born and raised on the moon, who might have very different ideas about governance and allegiance than the Earth-based companies and governments that founded the settlements. History offers instructive parallels. Colonies established by European powers eventually sought independence, often violently, when their interests diverged from the home countries. The American Revolution, independence movements in Latin America, decolonization in Africa and Asia, all followed this pattern. Would lunar history repeat it? The dynamics might be different because of the technological dependency. A lunar settlement couldn't survive without imports of certain goods from Earth, at least initially. But as they develop in situ resource utilization and manufacturing, that dependency decreases. If they're producing energy, water, oxygen, metals, food from local resources, what does Earth provide that's irreplaceable? Information, culture, genetic diversity through immigrants, certain high-tech components that are hard to manufacture locally. Those might not be enough to maintain control if the relationship becomes adversarial. A more optimistic vision is a cooperative network where Earth and lunar settlements, along with future Martian colonies and asteroid habitats, form a single civilization spanning the inner solar system. Free movement of people, ideas, and goods, with local autonomy but shared governance on issues of common interest like space traffic control, environmental protection, and resource management. This is the dream that many space advocates hold. Humanity united not by erasing differences but by expanding beyond our single planet, by becoming resilient through distribution, by having frontiers that pull us forward. Ask yourself this: would you go to the moon if you had the chance? Not as a tourist for a brief visit, but as a settler, knowing you might spend years there, might never return to Earth, might raise children in lunar gravity under artificial light? What would it take to make you say yes? Adventure, economic opportunity, escaping problems on Earth, contributing to something larger than yourself, the sheer novelty of living somewhere no humans have lived permanently before? Or would the risks and sacrifices be too great? The loss of everything familiar and beautiful about Earth, the trees, the ocean, the wind, natural light, the diversity of life. There's no right answer, but thinking about it reveals what you value and what drives human exploration. The psychological research on motivation for extreme environments shows that people who thrive are those with strong intrinsic motivation, a sense of purpose beyond material rewards. Money alone doesn't sustain you through hardship. Believing you're part of something meaningful does. The first lunar miners and settlers will need to be people driven by vision, by the desire to build something new, by the belief that making humanity multiplanetary is important. Selecting for those characteristics will be as crucial as selecting for technical skills and physical health. Training programs are already being designed. Analog missions in remote locations on Earth, like the Mars Desert Research Station in Utah or the HIC's habitat in Hawaii, simulate some conditions of living in isolated, confined environments. Participants spend weeks or months in these facilities, conducting research, maintaining equipment, dealing with simulated emergencies, all while cut off from normal life. The data gathered helps understand group dynamics, psychological stresses, effective habitat designs, and communication strategies. These programs will inform how we prepare people for the moon. One of the unexpected challenges identified in these studies is boredom. When you're in a small habitat with the same few people, doing repetitive tasks, entertainment options limited, the monotony can be crushing. Crews need adequate recreation, variety in activities, privacy when possible, and meaningful work. On the moon, the novelty of the environment might help initially, but it could wear off. Looking at the same gray landscape every day, even with Earth in the sky, might become just the view outside the window. Keeping people mentally healthy will require thought and resources. This brings us back to an economic consideration. What's the cost of supporting a human in space? Current estimates for the International Space Station are about $3 to $4 million per person per year when you factor in transportation, life support, food, equipment, and maintenance. That's obviously unsustainable for large populations. The cost must drop dramatically, which is why in situ resource utilization is critical. If you're producing oxygen, water, and eventually food locally, the main costs are initial capital and high-tech components that must be imported. As manufacturing capabilities grow on the moon, even those decrease. The goal is to reach a point where lunar settlements are largely self-sufficient, trading specialty goods and services with Earth rather than depending on constant resupply. Lunar agriculture is a fascinating challenge. Plants need light, water, carbon dioxide, nutrients, and suitable temperature. Light can come from sunlight via windows or fiber optics, or from artificial LEDs, which is necessary during the 2-week lunar night. Water can be extracted from local ice. Carbon dioxide can be captured from human respiration or imported initially. Nutrients are trickier. Lunar regolith lacks the organic matter and biological complexity of Earth's soil. You'd need to process it, add nutrients. Perhaps use hydroponic or aeroponic systems where plants grow in nutrient solutions without soil. Waste recycling becomes crucial. Human waste provides carbon, nitrogen, and other nutrients for plants. It's a closed-loop life support system where nothing is wasted. Researchers have grown plants in simulated lunar soil, demonstrating it's possible with the right amendments. Some plants, like certain weeds and hardy crops, can tolerate the conditions better than others. Initially, lunar agriculture would focus on easy-to-grow, nutrient-dense foods. Lettuce, tomatoes, peppers, herbs, perhaps potatoes or sweet potatoes. Over time, as expertise and infrastructure grow, the variety could expand. Fresh food is not just nutritional, it's psychological. The smell of growing plants, the taste of fresh vegetables, the greenery, all contribute to mental well-being. There's even discussion of eventually producing luxury goods on the moon for export to Earth. The logic is that anything made on the moon has rarity value. A bottle of wine fermented in lunar gravity, an artwork created by a lunar artist using local materials, jewelry made from lunar metals and minerals. These could command premium prices from collectors and enthusiasts on Earth. It's a niche market, but markets have been built on less. The first lunar-grown food sold on Earth would be a novelty worth far more than its nutritional content. We should address a question that often comes up. What about the debris and space junk problem? Every launch adds potential debris. Satellites fail and become junk. Collisions create thousands of fragments. The more activity in cislunar space, the greater the risk. This is a legitimate concern. The Kessler syndrome, proposed by NASA scientist Donald Kessler, describes a cascade where collisions create debris, which causes more collisions, exponentially increasing junk until certain orbital regions become unusable. Low Earth orbit is already crowded. Extending heavy industry to the moon means more traffic, more potential for accidents. The Artemis Accords address this by including commitments to properly dispose of space objects and mitigate orbital debris. Technologies are being developed for debris removal. Nets, harpoons, lasers to nudge debris into decaying orbits, robotic arms to capture defunct satellites. The key is to manage space as a shared environment with rules and enforcement. Unlike Earth, where regulations often lag behind problems, we have the chance to be proactive in space, establishing good practices before the environment is irrevocably damaged. The economic incentive helps here. Companies and nations want space to remain accessible because their investments depend on it. A debris cascade that makes lunar orbit unusable would destroy trillions in assets. Self-interest aligns with environmental protection, at least in this case. That doesn't mean it's guaranteed. Tragedies of the commons happen when individual incentives diverge from collective good. But the high-stakes nature and the relatively small number of actors initially means coordination is more feasible than managing, say, ocean pollution or atmospheric carbon. Let's contemplate the timeline again, but from the perspective of a child born today. If you're born in 2024, by the time you're 10 years old in 2034, there might be astronauts living on the moon for extended periods, mining operations underway in demonstration phase, and regular cargo flights delivering equipment. By the time you're 20 in 2044, you could be applying for a job with a lunar mining company, planning to spend a few years working there, earning a high salary to pay off student loans or save for a house back on Earth. By the time you're 30 in 2054, lunar settlements might have populations in the thousands, children growing up there, a genuine frontier economy. You could emigrate, start a business providing services to miners, maybe a restaurant or entertainment venue, or a consulting firm helping new companies navigate lunar regulations. By the time you're 50 in 2074, the moon could be a major economic hub, fusion power transforming Earth's energy landscape, asteroid mining operations launched from lunar facilities bringing back resources, Mars colonies being supported by lunar infrastructure. You might retire comfortably on investments you made in lunar real estate or mining stocks decades earlier. Or maybe the whole thing develops slower than predicted, and by your 50s, we're just getting to the point optimists thought we'd reach in the 30s. History doesn't follow projections neatly, but the trajectory is toward expansion, toward utilizing space resources, toward becoming a multi-planetary species. The question is pace, not direction. What about catastrophic risks? Space is unforgiving. Accidents will happen, and they'll be deadly. The Apollo program had the Apollo 1 fire that killed 3 astronauts during a ground test. The Space Shuttle program lost Challenger and Columbia with 14 crew. Russian and Soviet programs have had their own tragedies. Lunar mining will undoubtedly see accidents, equipment failures, habitat breaches, people caught outside during solar flares receiving lethal radiation doses, explosions in processing facilities. How we respond to these tragedies will test our commitment. Will we accept the risks as part of pioneering a frontier, or will public outcry halt programs? The answer likely depends on the context and how risks are communicated. Interestingly, dangerous occupations on Earth, from deep-sea fishing to logging to mining, continue despite high fatality rates because people understand the risks and choose to accept them for the rewards. If lunar mining is positioned similarly, as a dangerous but voluntary and well-compensated profession, public tolerance might be higher than for programs perceived as vanity projects. Transparency and informed consent become essential. Workers and their families need to understand the risks clearly, not have them minimized or hidden. Insurance and liability present interesting legal puzzles. If someone dies in a lunar mining accident, who's liable? The company that employed them, the nation that licensed the company, the equipment manufacturer, multiple parties. What laws apply? What court has jurisdiction? Families seeking compensation might find themselves navigating unprecedented legal territory. Proactive establishment of clear frameworks, perhaps an international tribunal for space-related disputes, would help. The United Nations Committee on the Peaceful Uses of Outer Space could serve this role if given appropriate authority and resources. There's also the question of rescue. If a habitat fails on the moon, if people are in danger, who is responsible for mounting a rescue? Is it the company's responsibility, the home nations, the international communities? The Artemis Accords include a commitment to provide emergency assistance, but the practicalities are daunting. A rescue mission to the moon would take days to organize and launch, even in the best case. By the time help arrives, the crisis might be resolved one way or another. This argues for redundancy and self-sufficiency in lunar facilities. Multiple habitats so if one fails people can evacuate to another, extensive life support margins, well-stocked emergency supplies. The inspiring counterpoint to these dark scenarios is the ingenuity and courage humans have demonstrated repeatedly in crises. The Apollo 13 mission, where an oxygen tank explosion crippled the spacecraft on the way to the moon, could have been a disaster. Instead, through creativity, determination, and teamwork between the crew and mission control, the astronauts made it home safely. That spirit, applied to lunar challenges, gives hope that we can manage the risks and respond effectively when things go wrong. Now, let's talk about something that might seem peripheral but is actually quite important. What we call things. Names shape how we think. The minerals and features on the moon currently have names assigned by the International Astronomical Union, mostly Latin terms or tributes to scientists and astronauts. As mining begins, will deposits and facilities get corporate names? Will we have the ExxonMobil Shackleton Crater Mine, the SpaceX Helium-3 extraction facility? This bothers some people who feel that celestial bodies should be free from commercial branding, that there's something tacky or sacrilegious about it. Others argue it's harmless and even beneficial if it encourages investment. There's no consensus. More significantly, will we start thinking of the moon not as the moon, that singular companion Earth has always had, but as Luna, a place, a world, perhaps eventually a nation or collection of nations? The shift from the moon to Luna in language would parallel the shift from abstract object to inhabited location. It's a small thing, but language reflects and shapes reality. Paying attention to these cultural shifts can tell us a lot about where we're heading. Art and media will play a role too. Just as the exploration of the American West inspired paintings, novels, and eventually films that shaped how generations understood that period, lunar exploration will inspire creative works. We're already seeing this with movies like Ad Astra and Moon, novels like Artemis by Andy Weir, video games set on the moon. These fictional explorations let us imaginatively rehearse the future, consider possibilities, work through concerns and hopes. The narratives we tell about lunar mining, whether they're optimistic tales of adventure and progress or cautionary stories of exploitation and disaster, will influence public perception and policy. Education is another critical piece. The next generation needs to understand space, not as a distant abstraction but as a domain of human activity. STEM education, particularly engineering and planetary science, will be crucial for supplying the workforce this industry needs. But equally important is civic education about space policy, ethics, and governance. An informed public can make better decisions about how we approach this transformation. Consider engaging with this yourself. Ask your representatives what their positions are on space resource utilization, on international cooperation versus competition, on environmental protection for celestial bodies. Support educational programs and institutions working on these challenges. If you have investment capacity, research companies involved in space industries, your capital can influence what gets developed and how. If you're a student, consider careers in aerospace, planetary science, space law, or the many fields that will support this industry. If you're a creator, make art that explores these themes thoughtfully. Every role matters in shaping outcomes. Here's a provocative question to end on. Should we do this at all? We've outlined the potential benefits, the economic opportunities, the scientific discoveries, the expansion of human civilization. But is it worth it? The resources invested in lunar mining could alternatively be used to address problems on Earth: poverty, disease, climate change, education. Some argue that spending billions or trillions to mine the moon when people on Earth are suffering is morally indefensible, a misallocation of resources driven by greed and escapist fantasies. They say we should fix our own planet before expanding to others. The counter-argument is that it's not either-or. The global economy isn't zero-sum. Space development can generate wealth and technological advances that benefit Earth. Solar power satellite technology developed for space could provide clean energy at home. Life support technologies could improve water purification and agriculture in harsh environments. The inspiration of frontier exploration can motivate young people to pursue science and engineering, creating human capital that solves all kinds of problems. And philosophically, expansion is part of what we are. Exploration is a human drive. Suppressing it to focus only on existing problems might actually decrease our capacity to solve those problems by stifling innovation and aspiration. Personally, each person has to weigh these considerations based on their values. There's no objectively correct answer, but the decision is being made through thousands of individual choices by engineers, investors, policymakers, and voters, whether we explicitly think about it or not. Being aware, being intentional about those choices, is better than letting them happen by default. As we stand here in the mid-2020s, looking up at the moon, we're at an inflection point. For all of history, the moon has been unreachable, a symbol, a light in the sky. In a single human lifetime, it went from unreachable to briefly visited and then neglected. Now it's becoming something new, a destination, a resource, a frontier, perhaps eventually a home. The trillion-dollar industry isn't speculation. It's emerging in real time. The companies are forming, the technologies are maturing, the missions are launching. Within a decade, the first resources will likely be extracted. Within 2 decades, a lunar economy may be functioning. Within 3, there could be thousands of people living and working there. This is the opening chapter of a story that will unfold over centuries. We won't see the ending, but we're here for the beginning, and the beginning matters enormously because it sets patterns, establishes norms, determines who benefits and who doesn't, shapes whether this expansion represents humanity at its best or worst. That's why this topic, mining the moon, is so captivating and so important. It's not just about resources or technology. It's about who we are, what we value, and what we're becoming as a species taking our first real steps beyond our cradle. The moon hangs there, patient and ancient, waiting. It's waited 4.5 billion years. What we do in the next few decades will determine what the next billion years look like, not just for the moon, but for us. The treasure is real. The challenges are immense. The stakes couldn't be higher. And the story is just beginning.